Hi, I am Shivji, and together with my colleague Sachidanand, I'll be talking about a story of our app re-architecture, where the app depends on Druid for its database backend, and we will explain how our app architecture to ingest data into Druid once per 3 hours to once per 5 minutes, stressed Druid, and how Druid configurations and some novel engineering helped us to get back and get to a happy state of Druid once again. First off, legal disclaimer, where we basically say that the things that we present here are our own opinions and we do not represent Nutanix Corporation in official capacity. I am a regular software engineer and a speaker. I also organize some meetups, case in point being our recent first in-person meetup on Druid in India, which was actually quite great. We had around 130 people attended, some amazing speakers, quite a good experience. I am excited about distributed databases and streaming, and I love open source software and communities. Sachidanand, would you like to introduce yourself next?
Sure, Steve. Hi everyone, this is Asidanand. I work at Nutanix Cloud Data Platform team. I love open source. I love distributed systems. Mainly, I work on distributed OLAP databases like Druid and ClickHouse. I am also an open source enthusiast. Over to you, Steve.
Thank you, Sachidanand. So let's get started. Contents. So what we present here is we will go very quickly talking about Druid, its architecture, how we re-architectured our app, which basically changes how we expect things out of Druid, the impact that had on Druid components, how we got the Druid components back again, and what about the bugs that we encountered. So let's start the journey. Druid 101, it's an amazing open source OLAP database, Apache 2 license under Apache Foundation, etc. If you're at Druid Summit, you probably know most of the smaller details that we have here. So we'll just keep moving very quickly. What we love about Druid is its modularity. Amazing lesson in modularity, really. Durability with S3 integration is something that we use a lot. It just simplifies so much. SQL for querying and the admin dashboard actually helps us debug a lot of things pretty quickly. If you look at the components that make the Druid database, first, historicals, where data is stored in the form of immutable segments that help it serve data for queries very fast. Middle managers are responsible for ingestion. Overlord will actually talk to middle managers and ask it to perform an ingestion task. Middle manager, if you look at it one more level deep, will actually go ahead and spawn a JVM task called peon. That is the actual thing that will execute your ingestion task. Coordinator will coordinate between historicals. Zookeeper, like you see here, is the one that will do cluster coordination between middle managers, between historicals as well as brokers, as we will see next. For metadata storage, Overlord and Coordinator use Postgres in our case. For deep storage, we talked about S3 integration. We love S3 for its availability and scalability, and we use that here. So our segments will effectively be on deep storage, and we then spread over historicals for faster access. Brokers are the ones that you reach out for queries. Router, in case you have a high scale deployment, is great to use, but that's optional. Like I said earlier, Zookeeper is used for cluster coordination, but in addition to that, it also provides service discovery as well as broadcasting when you are done with your own tasks, etc. You can write streaming data. Case in point, Kafka Druid ingestion actually works pretty well. You can also write data in the batched form. When you write, you talk to the router. Router gives your ingestion tasks to overlord. Overlord will ask middle managers to perform ingestion, which will make segments, keep them on deep storage, and get them available on historicals. When you query, your client will fire a read query on router again. That will reach broker in this case. Broker will get historical data from the historicals and some of the latest data that has not reached from middle managers via deep storage to historicals. For that data, broker will also get data from middle managers, and both of these data combined reaches broker. It will merge all that and give it back to you in a form that you look at on your client. What about our apps? What we do in the app is basically we have an analytics dashboard which gives people view into their network packets flowing between different IPs. So different VMs there, how data flows between them through IPFix log files is what we do. So we have collectors which will collect these and via some other services in between enrich that data. And then this enriched data gets into S3. Druid ingestion happens from S3. And Druid basically forms the backbone to provide data to our analytics dashboards as well as ML engines. Talking of our scale, 18.5 TB of data, 294 data sources. If you look at last 24 hours, 423K tasks, pretty much 8 million queries in last 24 hours. If you look at total queries per hour, the peak is somewhere around 400K tasks submitted per hour, again 18 to 20K in peak workload. Talking of data model in our app design, and I'll actually show you architecture diagram for the same, but going over some context before that, we are providing an analytics dashboard where our customers can, using some filters on the UI, slice and dice the data that is coming from Druid. Multi-tenant use case, for every customer, every use case, we make data source in Druid. Pretty much that, plus some other bit of engineering. But for simplicity, let's say that. And when we do a bigger re-architecture, Druid upgrades and stuff like that, we roll out things in a phased manner. I'll show that going ahead again through a small animation. And our workflow engine that forms the basis for our ingestion pipeline is backed by temporal. And in between, we also have some Java-based workers which use Postgres for storing state. So this whole story, like I said, started with app redesign, which comes from change in our requirements from the product side. We had an SLA saying the IPFix logs from now can be shown on our analytics dashboard within 3 hours. The SLA has actually reduced to a worst case of 15 minutes. We actually tried to get all that data available in Druid within 5 minutes, close to 5 to 6 minutes actually. And the release plan, like I said, in a phased manner. So this is something that shows our old architecture. We are an infrastructure company that provides VMs for our customers in their data center. We analyze the IP flow logs if customer wants us to do that. Our data collection agent actually gets data. These are IP flow logs. These flow to S3 buckets. And from S3 buckets, that will get loaded into Druid. The way this happens is we used to have a cron that comes up every 3 hours. It triggers the ingestion pipeline backed by temporal. And this pipeline will actually nudge Druid to go get data from S3. Druid now powers our analytics dashboard as well as our ML engines. The new architecture actually to serve an SLA of a worst case of 15 minutes, we have the same cron operating every 5 minutes. Now this cron is held inside the agent itself. So every 5 minutes, this agent will get IP fix logs and put it into S3 buckets. Every time it does that, once the data has been put into S3, it will nudge the ingestion pipeline. If the ingestion pipeline, depending on its configuration, wants to ping Druid now or maybe in the next batch, depending on the amount of data it has got, basically our ingestion pipeline actually has a lot under the hood using the Java workers that we talked earlier. It's a state machine backed by temporal, and it can actually absorb back pressure quite well if there are problems in anywhere else down the pipeline. So this ingestion pipeline will actually put data from Druid to Druid from S3 buckets, and the rest of the thing, analytics dashboard and ML engine actually remains same. What we effectively did there, if you look at it from the Druid lens, is we are sending a lot more tasks, but earlier our tasks would be bigger but fewer. Now in the new design, we have a lot of tasks, but these are smaller tasks because these are IP flow logs only for 5 minutes as against 3 hours earlier. I talked about the phased rollout. What we basically do is on the new features or new version of Druid, whatever, we put one data source. If it all looks good, more data sources, and eventually every one of them. When we did that here, initially it was fine, but when we put all the data sources with this new app architecture, Overlord actually started complaining, saying too many tasks. It actually got stuck. So wouldn't assign any tasks to middle managers. And like you see here, this is the proof of the pudding. You have the Druid dashboard saying pending tasks are 22K at this point, but it kept increasing forever. If you look at our monitoring dashboards, specifically overload process, the total task would be somewhere around 2K. And now after the re-architecture, a lot of smaller tasks. So the total task actually obviously increased. It now gets all the way from 2K to something around 10 to 12K. Overload process actually has a lot to do. Obviously, CPU usage was quite under control, but it went all the way till 100. And that's why the tasks are not getting assigned. Overload is completely stuck. And this is a summary of the same, where our tasks were not being executed and they were not progressing at all. No update in tasks. Sachin, you want to go ahead, share your screen and then present the story of how we got back component by component and the configurations we changed.
Yeah, thanks, Shiv. So I will go through how we got our overload alive. So as we already saw, there was 100% CPU usage and the tasks were now 12x as compared to the previous. So first thing that comes to my mind when I look into this is I can go for a bigger size of overload. As we know, overload is not horizontally scalable. We need to scale it vertically. So we went for a bigger VM. This didn't help much. Already after that, we tried some configs which helped a bit, but eventually we ended up having a bigger DB instance. So I will discuss about the DB changes later. So first, what we tried with the overload is Druid indexer runner type. So this basically determines how overload and middle manager will talk to each other. So Druid has few mechanisms. One, it is through Zookeeper. Another, it is through HTTP protocol. In the older versions, Zookeeper was default. Now, with the latest versions, we have HTTP remote, which uses HTTP protocol while assigning while overload is assigning the task to middle managers. This helped us a bit. After that, there is another setting called queue.max size of the overload. So the default value of this is integer.max value, which is like almost infinity. So now when we set it to, let's say, 5,000, when we submit a task and already there are 5,000 concurrently active tasks in Druid, it will just throttle it. It will reject that, but the overload will not die. This helped us a bit. After that, we applied one more optimization, which is looking at the number of pending tasks per data source per interval. As we know, we have one data source per customer. So with this API, we can get the number of pending tasks for that data source. From that, we can determine for the interval which we want to submit whether it has a pending task. Depending on that, we will not overburden the overload, and that helped us reduce load and overload. So for this, we filed a few bugs on open source Apache Druid. As you can see, the first one being overloads stop responding, and the second one being it throws 500 internal server error, which is misleading when the queue max size has reached. So for that, recently I raised a PR and currently it is merged. So now the overload, basically the Druid will send HTTP 429 too many task error, which is the appropriate error in this scenario. So now coming to the DB, as I already told, the DB, after applying all the overload optimizations, we came to know that DB is the bottleneck. When we query for a task status, when the overload is asking for a task status to Postgres, it was taking too long time. So what we did was we increased the instance type of Postgres. This resulted in good things. One, we got overload CPU utilization less, number of pending tasks decreased, and the task load utilization graph, which is a overload matrix, that now looked much better with close to 90% of task load utilization all the time. Previously it was less than that, which is not ideal. So after we stabilized our overload, we saw that tasks are now getting assigned to middle manager slots. So middle managers are basically have peon processes, a fixed number of peon processes, which will take up tasks from overload. So here, what we did first was we added more number of VMs to get more slots. So this will help us getting more tasks processed concurrently. This After this, what we saw was as we are getting less number of files per task, we can so now the task resource which it needs is small. So what we did was we tiered the compact task and index task into two tiers. Now the compact task can go to the middle managers, which has peons with more resource, and for the index task we don't need that much resource as compared to compact task. So for that, what we did, we separated compact task and index task. We added more slots to the index task tier. With that, we also right sized our middle managers. With all these optimizations, now the middle manager and overload overall ingestion pipeline looks stable. This shows a summary of that. So at first we had 12 mm with 5 slots. We increased it to 24 mm with 5 slots, which was good, but it was having more cost. So we reduced the number of slots. We increased the number of slots and reduced the number of MMs. So after that, we tiered those 12 MMs into 10 in index task and 2 in compact task. So with these optimizations, our ingestion pipeline got stable. Once our ingestion pipeline got stable, we faced issues in coordinator because the middle manager producing too many segments, which are in turn putting pressure on coordinator to assign. So in our Druid cluster, we have now too many segments. So as you can see, our number of unavailable segments count kept on increasing. It reached close to 1.5 lakh. So the historicals are now deprived of latest segments and the queries are not served properly. So to summarize the coordinator crisis, we have huge number of small segments, unavailable segment count increased, coordinator CPU usage was high, and coordinator cycle is taking too long time. For this, here also the first things comes to our mind is we are getting a bigger instance for the coordinator process. So this helped in minimizing the CPU utilization, but we didn't get much improvement in the coordination cycle. So we have now the same big DB, and we tried few coordinator dynamic configs to reduce the number of segments per coordination cycle. So Druid has one dynamic config called percentage of segments to consider per move. We have set it to 25%. By default, it is 100%. Let's say we have 10k segments, then Druid will only consider 2.5k segments out of that. To further cap the number of segments per cycle, we set the max segments to move parameter to 1000. So we will only consider 1000 segments at a time. So with this, now we have reduced the number of segments, the load on coordinator. So one more parameter we tried was round robin segment assignment. With this setting, what coordinator will do is it will first assign all the segments to all the historicals in a round robin fashion, and later it will lazily assign according to our balancer strategy, which is cost by default. These three settings helped us in reducing the time it takes for completing the coordination cycle. So now our coordinator was stable. One more issue we saw in our compact task here is we have set the in versions older versions of Druid, we need to set the input segment size for compact task. That is the combined size of all segments that it is compacting. So with the later version 23 onwards Druid version, this setting is increased to 100 TB. So there is a design change. So now the Druid compact task only downloads the needed segments while doing a compaction. So this also helped us in removing our compact task failures. So with all these optimizations, the coordinator is now stable. Now we come to the historicals. So we have auto compaction on our Druid cluster enabled. That means after a certain offset, let's say it is 2 days, older segments which are greater than 2 days, those will be compacted to higher segment granularity. So the cold data will have higher segment granularity where compaction is done, and hot data will have lower segment granularity which is not compacted yet. So our historicals will need accordingly some more processing powers to when there is a query issued for the recent data. So accordingly, we need to decide how much processing power it needs depending on our offset. So with all these optimizations, our Druid cluster returned to happy state. So to summarize all these learnings, what we got is like we stabilized our Druid ingestion and query pipeline and onboarded all customers in a phased manner. We set the optimal queue size after some trial and error to observe the initial burst of tasks. When we were doing all these changes, we increased the MM count. We right sized the overload and coordinator, which we increased during the initial design changes. And one more thing is to know very carefully, like all the overload and coordinator dynamic configs, as they are not horizontally scalable. We need to apply them very carefully. With that, now we are towards the end of the talk. We are open to questions.
In case you want to send us questions later, we also have put our LinkedIn URLs. These slides will be available on the SlideShare account that I mentioned here, and you can look at our LinkedIn later. So keep the questions coming now if you have any of them, or you can also send those to us later. Thank you.
Thank you, everyone.